Good day, folks. Welcome to Bright Mind Academy, where we bring brilliance to every lesson. Now, let's continue with May June 2022 question paper. Now, question 4, momentum and impulse, right? Yes. Now, 4.1 starts with us saying what is meant by an isolated system. Remember, an isolated system in physics, we say now it is a system, okay, a system in which the net external force it is zero. It is equal to zero. Okay, a system in which the what, very important, the net or the resultant, the net external forces, okay, the or force is zero. This is very important. Very important. Net external force is zero. Now, it is a system in which there are no friction, there are no applied force, there are no tension force. It is just a system on its own and its internal forces. All right. Yes. So it is a system in which the net external force it is equal to zero. Since we say it is now isolated from other, from what it is isolated from other forces such as friction, and tension, applied force. Yes. Even if they were to ask you, is this system isolated? If there is friction, no. Why? There is an external force. If there are no friction, no external force like applied force and tension, when they ask you, is this system isolated? Yes. Why? There are no external forces. This is nice. This is nice. Now let's move on to now a nice stuff. During an experiment, a rocket of unknown mass is mounted on a toy car of mass 20 kg. You can see that, right? The rocket combination moves at a constant speed of 2.5 meters per second along a horizontal floor. After a certain time now, or after a certain instant, the rocket is fired horizontally in the direction of motion at speed of 30 meters per second. As a result, the car slows down to a speed of 0.6 meters kanjalo. Okay, we see that ignore frictional effects. Now, okay, it is isolated, yes. Remember this topic, it is momentum and impulse. I want you to consider these three cases. We have these three cases where before and after. Ne? Okay, let me do this. Consider these three cases before and after. Okay, for case one now. For case one, what happens? Nope. For case one, we have an object A moving towards that side, and object B moving there with different velocities, right? And now after collision, it moves. Ball A moves opposite, and ball B moves wherever. Okay, but now the important part is that their momentum, before they had their independent momenta. There is no momentums, it is momenta. They have different momenta, right? And after the collision also, they have different momenta again, because now they are moving with different velocities and their respective masses, right? Case 2. Case 2. Case 2, it is where ball A now meets ball B. Okay, can you see before they have different momenta, right? Yes, but now after collision, it happens that now they stack together, they're off, and now they move with the same velocity. Can you see now they share the momentum rather? Okay, so now they move with the same velocity, they're off. Okay, this is case 2. Case 3, it is when now we call this one not necessarily, these are collisions, okay? But the one I'm going to do, we do not necessarily call it collision. It is what? Explosion. Now, I can say, if I have one, I like to do an example with a gun. A gun, I don't know how to throw a gun, but yeah, a gun there and a bullet, okay? And a bullet there, okay? A gun and a bullet there. Now, what happens? Can you see now that their momentum, this mass of a bullet plus mass of a rifle, yes, this is a rifle, they are combined and they have the same velocity. Can you see that? But now if they are at stationary, it means they do not have any initial momentum, right? But now I want you to see something. When you pull the trigger, what happens now? The rifle will move backwards. Okay, that's what the gun does. Okay, I'm sorry, I do not know how to draw. The gun will do what? The gun will move backwards. Okay, that's what happens after shooting. Okay, but what will happen to the rifle? Can you see now the oh, sorry, not the rifle, the bullet. The bullet will move towards the right with a velocity thereof. What I'm trying to say is that initially they had their momentum combined, again, then after they had their a different momenta thereof. Okay, so it means for case one, I like to simplify formulas. For case one, the formula that you use, you'll say momentum of A plus momentum of B. You'll state these are the initials, right? It is equal to momentum of A plus velocity of A final plus momentum of B, velocity of B final. Okay, yes. For case two, what happens? They move with a different momenta, right? Initial. But now what happens? They combine after the collision. So now after the collision, they combine. It becomes what? Mass of A plus mass of B. They move with the same velocity final. Then for case 3, what happens? For case 3, they start with themselves being combined again with the same final velocity. But now after that, what happens? They move with different velocities thereof. This is B, sorry. Final. This is what you can maneuver your equations around when doing any calculations. Okay. Yes. Now let's clear up that and answer the question. This is supposed to be a short video because now it has a short questions thereof that needs to be answered thereof. Okay. Yes. Now without wasting any further time, let's just dive into them. Okay. Yes. Now, uh, can you see now this they are combined now? This is a type of a collision. Why am I saying it is a collision? Because they start together. Okay. Now let's see. When they start together, now their mass are combined. Okay. But now they are moving with the same velocity. Okay. But now after that, after the collision, what happens? This one, can you see they were moving at the speed of 2.5, but can you see now the speed of this one, it is now 0.6. The case that it moved it back a little bit. Okay, but now since well it had a greater momentum, it managed to do what? To still move forward, but now with less velocity. But now this one accelerated. Can you see? Now, okay, 4.2 says to us, use relevant physics principle to explain why the firing of the rocket will slow down the card. Now, why firing this one will slow down the card? Now, the easy one you can use it is Newton's third law. Why? When this one applies a force on the rocket to make it move towards the right, so it applied a force. This is the force of the what's this? The card on the rocket. Okay, the force of the card on the rocket. Is it the card? Yes, the card, if I'm spelling it correct, on the rocket, right? But now, according to Newton's third law, is that the card the rocket rather will exert the same force on the rocket Oh, this English is running away. On the rocket, but in opposite direction. So this one will be the force of the rocket and the card. So hence now this one will try to move a little backwards, but due to the momentum that it had before, or the force it had before, it is greater, so it still continues to move uh, forward, but now with a decreased velocity, because it was trying to slow down. Okay, or rather, this force was trying to slow it down. Okay, so the first one that you can use, you can say, uh, according to third law, according to Newton's third law, what happens when the rocket exerts a force on the card? the cart will exert the same force but in opposite direction to that of the of the uh, of the rocket. Let me put it in wording. You can say the rocket exerts a force on the trolley, on the toy cart, right? Yeah, to the opposite, to the opposite. I don't know, but okay. Now I would say Newton's third law. Then I'd say the the rocket will exert a force, a force on the cart to the left. That is towards the left. Why? Because this one it is exerting a force towards the right, so this one will exert a force towards the left. Another thing that you can use, it is now the impulse or the momentum. Now, if this one has a momentum, uh, remember momentum is conserved in this case, the off, right? So whatever the change in momentum that this one has, this one will have an opposite of that momentum. Okay. Similarly to the impulse, if this one acquires an impulse of a positive impulse, this one will have a negative impulse of that. Okay, yes, because now the system is conserved. Remember when I add those momentum, change in momentum, they should give me zero. This and this, they should give me zero. Similarly to the impulse, they should give me zero. Okay, this is the reasoning that you can use. Okay. All right. All right. Now let's move to interesting stuff. The calculation. Do not neglect the theory around behind physics. You're gonna get most of your answers incorrect because yeah, it is very important to learn. Okay. Now that we know momentum is conserved in this case, now they say to us, calculate the mass of the rocket at the instant the rocket was fired from the toy car. Okay. Okay, it's fine. Let's just use momentum here. But remember, for this case, I say now you'll use this formula. Say it is the mass of the cart. Okay, mass of the cart plus mass of the rocket. Then they move it the velocity initial. Okay, it is equal to the what? Now they move independently of each other. You can say mass of the cart, velocity of the cart, final plus mass of the rocket, velocity of the rocket, final. Can you see now? This is 1 mark, okay? But you can also start here. The sum of momentum initial or before the collision, it is equal to the sum of momentum after the collision, okay? Now we can substitute. Now, what is the mass of the cart? We were given the mass of the cart as 20, okay? 20, but we are looking for the mass of the rocket in this case. What was their initial velocity? Their initial velocity was 2,5. Again, their initial velocity was 2,5. It is equal to what now? It is equal to a mass of the cart. It is 20 multiplied by. Okay, let's choose going to the right as positive. Choice of direction is very important. Now the cart is also moving to the right again with 0.6 meters. Okay, so we'll just say 0.6 meters plus mass of the rocket is what we are looking for the sorry, mass of the rocket. Then what is the velocity of the rocket? It is 30. Now you do your mathematical gymnastics. Okay, it's fine. Let's simplify math. 20 multiplied by 2.5, I think it's something like 50. Let's just confirm that. 20 multiplied by 2.5, yes, it is 50 plus 2.5 mr. It is equal to 20 times 0.6. It is 6 divided I think something like 12, 1.2. 20 multiplied by 0.6, it is 12. Okay, 12 plus 30 mr. Okay, then I'll take mr to the other side and watt to the other side. So I have 50 minus 12, it is 30, 38, I think. Then 30 minus 2.5, I think it is something like 27.5 mr. Then you know how to find the mass of the rocket thereof. Remember, it is physics, it is in kilogram. Okay, so let's confirm the answer thereof is going to be 38 divided by 27.5. I get a perfect number of 1,38 what kilogram. So yes, that's all for momentum and impulse. It was supposed to be a short video now, but I needed to explain something. Okay, so yes, let's meet on question 5, work, energy, and power.